Howdy, everyone. Happy Monday. Happy Ides of March. As you can see from this slide, Texas is a good place to observe mathematical functions. I hope you enjoyed the weekend, and in particular, hope you did something mathematical on Pi Day yesterday, March 14th, 314. As you probably know, March 14th was also the birth date of Albert Einstein. He would have been 142 years old yesterday. Yesterday would have been the birthday of Stephen Hawking. Many people consider him the best astrocosmologist that there has been. In case you haven't been over to the physics building, the George Mitchell physics building, the lowest floor has an auditorium called the Stephen Hawking Auditorium. Back in the 1990s and early 2000s, Stephen Hawking made many visits to A&M. I had several occasions to meet with him, even took him to Pi R Square to get a cheeseburger one time. So that was one of his favorite foods. A couple more chat comments. Let's see what they are. Okay, Aggies are sawing the functions off in some cases, but that song is a little bit less appropriate since the Aggies don't play UT anymore in football games, at least. Okay, so starting with that, we can now go on to physical chemistry lecture. And we finished rotational spectroscopy last time. Mostly we talked about diatomic molecules. And then I pointed out what kind of information you could also get on polyatomic molecules. But the structures of a very large number of polyatomic molecules have been determined by rotational spectroscopy. The picture I'm showing you now is that of E. Bright Wilson. Bright was actually his middle name, and he was indeed very bright. And he was one of my scientific heroes. And when I was in graduate school, the research group that I was in under Richard Lord at MIT and the one of Bright Wilson at Harvard, we would meet several times a year to discuss spectroscopy. So I got to know this fellow quite well. I always felt that he should have received a Nobel Prize in physics or chemistry for his work in vibrational spectroscopy. And the fellow that wrote the physical chemistry book that I'm taking this picture out of also thought very highly of him, and therefore put his picture at the front of the chapter on vibrational spectroscopy. Some of you are probably familiar with the Welch Foundation. This is a wonderful foundation which funds research only in the state of Texas and only to chemists. That includes chemical engineers and biochemists, or even physicists if they have enough of a chance to get chemistry into their work. Well, why I mentioned the Welch Foundation, I and many other professors have grants from them, but they also give an annual award, which is sometimes called the Mini Nobel Prize. And Bright Wilson in the 1970s, I believe, received the Welch Foundation Award for about $300,000. So he didn't get totally ignored. If you read about him, it'll point out that he had a son who did receive the Nobel Prize in Physics in 1982. And the Nobel Prize, of course, to scientists is very much like the Heisman for football players and such. So it's really a big deal when someone can get it. I want to tell you about Kenneth. So Kenneth was a young professor at Cornell. And as most of you know, for professors to get tenure, you have to prove that you're able to teach and also that you're able to do top quality research, or especially at places like at Cornell or A&M or Harvard, places like that. You have to prove that you're a good researcher. So Kenneth Wilson, Ebright Wilson's son, was at Cornell, and he'd gone 6 or 7 years without publishing a paper. Everybody was expecting him to do something brilliant, but he hadn't done it yet. And so the faculty at Cornell had a dilemma. Do we let him go and don't give him tenure, or do we take a chance that he's actually going to finish his discoveries? So they went ahead and they gave him tenure, and sure enough, within 2 or 3 years, he made his wonderful discoveries in physics. And by 1982, then he got his Nobel Prize. So that sounds like a good decision for Cornell, but once you're famous with a Nobel Prize, everybody would love to have you. And so Ohio State went to Kenneth Wilson and wooed him away and offered him fancy laboratory space and lots of money to do research. And so off he went to Ohio State. So it sounded like, again, Ohio State was doing pretty well by getting Kenneth Wilson. But after a few years at Ohio State, Kenneth Wilson decided he would like to improve K through 12 education in America. And so he decided to devote the rest of his life to that. And he wasn't particularly good at that, as it turns out. His heart was in the right place, but he didn't seem to be able to do much in that area. And he more or less quit doing physics. So it's kind of a story of how it goes for scientists. Sometimes you get great fame and then maybe wither away. Schrodinger, by the way, after he made his discoveries and stuff, he kind of would like to sit at his desk and ponder the universe, but did less science after the fact. Anyway, this fellow, Bright Wilson's one of my great scientific heroes. He wrote a book in 1955 called Molecular Vibrations, and much of our understanding of vibrations comes from him. Okay, so just as we did for rotations, when we talk about molecular vibrations, we'll start with a diatomic molecule model to look at how vibrations occur. And we've basically already done the quantum mechanics for this problem when we looked at the harmonic oscillator. So I mentioned several times that we can think of a chemical bond kind of like a spring. The molecule is vibrating back and forth much faster than a spring would, something like 100,000 trillion times a second. I think that's 10 to the 14th times per second. So what does the potential energy function actually look like? What does capital V look like for the vibration of a diatomic molecule? Well, the solid line here is a good indication of what it does look like. So as we talked about when we talked about molecular structure and diatomic molecules found an energy minimum, this potential energy curve shows that there is a minimum energy for the bond distance. The molecule is smart, it chooses that distance, and that's where its energy minimum is. If we push the two atoms together, the energy goes up to infinity as R approaches 0. The harmonic oscillator represents this actual curve pretty well. It's the dotted line, and especially on the low frequency side, the low energy side, the harmonic oscillator and the real curve look pretty good. The harmonic oscillator, however, says that when you try to pull a bond apart, the energy goes to infinity. So remember, the harmonic oscillator potential energy is 1/2 kx squared, and so this will keep increasing as a parabola does. A real molecule, when it vibrates, that's fine. But when you try to stretch it too far, at some point the two atoms just fall apart and you no longer have a molecule, and that's where you reach the dissociation energy. So by definition, if you go from the bottom of the potential energy curve to the dissociation energy, that's written as D sub E for dissociation energy. But there's also a more meaningful dissociation energy, since molecular vibrations have a 0-point energy. You remember we have a 0-point energy for harmonic oscillators. So the lowest energy a molecular vibration can have is here at quantum state V equal to 0, and it's about 1/2 the vibrational frequency above the bottom of this potential curve. So the real amount of energy it takes to dissociate a diatomic molecule is called D sub 0, and it's from the 0-point energy up to there. So the difference between D sub E, I guess here it's written D sub EQ from the equilibrium point. The difference between them is 1/2 of the vibrational frequency that we have. And the vibrational frequency is the amount of energy it takes to go from 0 to 1. This diagram shows you that there are higher quantum states. The harmonic oscillator, you'll remember all the quantum states are equally spaced. But in the real molecule, because the curve tails over like this, the quantum states start getting closer and closer and closer together. And this effect is called anharmonicity, or non-harmonicity, that you have for this particular case. As we'll talk about more, this transition 0 to 2, that's called the first overtone, and it's approximately double the frequency of the fundamental vibration. 0 to 3 is called the second overtone. So this is a lot like music, that when you double or triple your frequencies, you can have overtones, second overtones, and things like that. Okay, so a lot of this we've already seen when we talked about harmonic oscillators. So here's what we did when we went through the quantum mechanics. We said capital V was 1/2 kx squared. K was a force constant, which we said should be proportional to the strength of the chemical bond. And X is the displacement from equilibrium. So here I've written it as capital R minus capital R sub E, and that quantity squared. So that's the displacement from the equilibrium position squared. We looked at solutions for this problem. When we did the Plano harmonic oscillator, I initially had a mass hooked to an infinite mass, a brick wall, so we could put an M in the denominator up here. But for diatomic molecules, where both of the atoms can move, we have to put in a reduced mass. We defined this when we talked about molecular rotations, and it's going to become useful again for molecular vibrations. So for a diatomic molecule, it's the product of the masses divided by the sum of the masses. We've already looked at these solutions. The energy levels for the harmonic oscillator were quantum number little v plus 1/2 times h nu. And so you can never get rid of this 1/2, even though v equals 0 is the lowest energy. And so 1/2 h nu is going to represent the 0-point energy of the diatomic molecule that you have. And we've defined the vibrational frequencies. So this is called a harmonic frequency, 1 over 2 pi times the square root of k over mu. I think I'll have something on this later in the notes, but I want to point out that if you go to your book defines this as omega, and the omega is the observed frequency corrected for anharmonicity. So it takes into account the fact that the harmonic oscillator, it doesn't work perfectly. So if you compare frequencies in your book for different molecules to what I tell you, I like to use the experimental frequencies to do calculations. Your book converts these to what it says would have been the frequencies if the harmonic oscillator had worked perfectly. So that's not terribly critical for our purposes, but hopefully that might keep you from avoiding some confusion. Okay, selection rules for infrared or Raman spectra. Delta V is plus or minus 1. So in this diagram, it means we're seeing 0 to 1. And that's strictly true for the harmonic oscillator model. But if you take into account the fact that this potential curve shifts over, you can see these overtones. The first overtone is maybe 5% as intense as the ground state. The next overtone may be 5% of that. So they get to be very, very much weaker. And normally you don't learn a whole lot more from them. So very few people bother to look for anything other than delta V equal to plus or minus 1. And delta E is equal to h nu. So we learn the vibrational energy levels from the harmonic solution to the Schrodinger equation, and we can then figure that out. Once we get to frequency, notice that we can calculate what a force constant is for a diatomic molecule, and we're going to find that's characteristic of how strong the chemical bond is. Selection rule for infrared spectroscopy is you have to have a dipole moment change, and we've talked about that. I pointed out that you don't necessarily have to have a permanent dipole like HCl for this to take place. For Raman spectroscopy, you have to have a polarizability change. And that means if you zap the molecule with intense light, like a laser, the light has to be able to drive electrons to one side of the molecule. And it can only do that if during the vibration, the shape of the molecule changes. I'll give you examples of that later for polyatomic molecules. So for the symmetric stretch of carbon dioxide, OCO, where both of the oxygen outer atoms are moving away from the center, that has no dipole moment change. It can't be seen in infrared spectra, but it can be seen by Raman because the molecule gets smaller, larger, smaller, larger. So normally, if we want to analyze these rules, we would use symmetry properties. And as I've said several times, we don't have time to go into that in this course. Okay, well, the formula is up here. This would give frequencies in seconds to the minus 1. The unit we're always going to use is reciprocal centimeters, also called wave numbers. And then we write this as nu bar. The bar means we're taking the frequency divided by c, converted to units to wave numbers, and then this formula comes out to be 1 over 2 pi c times square root of k over mu. So most likely on your second exam, which will be 2 weeks from today, you will have a problem relating force constant to vibrational frequency, and this is the formula that you should be using. Okay, so back to this curve. Again, the difference between the dotted line, harmonic oscillator, 1/2 kx squared parabola, and the real molecule, that's called anharmonicity. And in order to account for that, a lot of people have played with functions. Probably the most famous of these is called the Morse function. And so mathematically, it's written like this. So you can see it gets a lot more complicated. We have the displacement from equilibrium in an exponential term. But the nice part is the potential energy does approach the dissociation energy as capital R goes to infinity. In other words, that'll make the exponential term drops to 0. And so we know that the solid nature of the curve will look just right here. It doesn't fit the rest of it perfectly, but work well enough that some people who like to look at overtones and so on utilize this. I think your book will talk a little bit more about this also. This little constant A here is written in terms of the vibrational frequency and the dissociation energy. And when you put this into the Schrodinger equation. You can't solve it exactly, but you can use a technique called perturbation theory, and you can show that the energy levels come out like this. And so there's a correction for the anharmonicity. And as I've mentioned, then your book will actually like to use what this frequency would be in harmonic terms, and then correct it to the observed one with this anharmonicity term. So again, this gets deeper into stuff when people take graduate courses in molecular spectroscopy or do research in this area, trying to understand potential functions. Okay, well, for your purposes, let's just look at how much effect anharmonicity does. So in addition to the Morse function, one could also write the anharmonicity expression as a Taylor series expansion. And in your notes that I'll show you later, I also show you what this can lead to get these appropriate results. Anyway, HCl, diatomic molecule, its real observed frequency is 2886 wave numbers for the vibrational transition, 0 to 1. If we had a true harmonic oscillator shaped like a parabola, every one of these spacings would be 2886. So like this. For the real HCl molecule, here are the spacing, 2886, 2783, 2679. So you can see it's like roughly 1 part in 28, or about 4% decrease in frequency for the next level, and then maybe another 4% decrease up to the next one. So then the anharmonicity is real, but whenever we want to do a force constant calculation, we typically always still use the slowest energy. Now, some people who would like to directly from the spectroscopy calculate the dissociation energy, it is helpful for them to look at many of these spacings, and then they can calculate d sub e from that Morse function, for example. Okay, so how do you find a force constant? This is our formula. I could put a big box around it, but this is the one you should use. Here is what you get when you square both sides, collect all the terms with the force constant on the right side. And all you have to do is plug in the numbers: speed of light, vibrational frequency, and wave number, reduce mass in grams. And I say grams because we use centimeters to the -1 for wave numbers. So we want to use grams, centimeters, second units when you do this. You're going to have access to your notes for the second exam, but if you didn't, I would tell you not to memorize this formula. I never memorize it. I'm afraid of getting something wrong. This one I remember very well on the left, and all you have to do is square both sides and collect terms, and you can calculate what the force constant is. Okay, so K we define as a force constant, and we've been basing it on the argument that a chemical bond is like a spring. But more correctly, it turns out that the force constant is actually the second derivative of the potential energy with respect to X, evaluated at the equilibrium position. So you take the derivative of the second derivative of the shape of this curve right here, and that's what a potential function is. So I'm telling you that for two reasons. You don't exactly expect the force constant to be directly proportional to the dissociation energy, but the rate at which this curve starts going up, which is what that derivative is going to be closely related to the dissociation energy as such. Okay, so there's a lot of little nuance in some of these features then as we look at it. All right, well, let's look at some force constant numbers. These are vibrational frequencies in wave numbers that are experimentally observed. If you read your book, it'll give you a somewhat different number. In fact, I have HCl 2886. I think your book will tell you it's something like 3,000 for the harmonic frequency, and then you have to subtract about 120 to get it to the observed frequency. So don't let that bother you when you see the different numbers. I like to go to these experimental values directly and then calculate what the force constants are. And you should be able to calculate all these numbers yourself. So that's a good practice problem. Just use that formula up above for force constant. All you need is the vibrational frequency. You do need to calculate what the reduced mass is to get that frequency. So let's look at these values. First one, I have H2. Force constant comes out to be 5.2 millidynes per angstrom. That's the same as 5.2 times 10 to the fifth dynes per angstrom. And if you multiply it by 100, you would get newtons per meter, which is the unit you have in your textbook. But spectroscopists such as I find it kind of silly to talk about how much force it takes to stretch a bond a meter when it's actually stretching something like a tenth of an angstrom. So these numbers make a lot more sense to people like me. Okay, so if we do H2, we get 5.2. D2 represents the heavier isotope of hydrogen, mass 2 hydrogen, deuterium, and we see its vibrational frequency drops to 2990. You calculate the force constant. As you expect, the bond strength does not change, and you still get the same force constant. So if you do a quick mental calculation for the reduced mass in atomic units, remember the reduced mass is the product of the masses divided by the sum of the masses. So for hydrogen, it's 1 times 1 over 1 plus 1. So that's 1/2. For deuterium, it's 2 times 2 over 2 plus 2. So that's 4 over 4. That's equal to 1. So the reduced mass of deuterium is twice that of hydrogen. And in our frequency calculation right here, you see the force constant relationship has a reduced mass here. So you wind up, let's look at this equation here. If you look at the relationship between frequency and reduced mass, you'll see there's a square root relationship. And since the difference between H2 and D2 is 2, you expect square root of 2, or 1.414, to be the ratio between these two numbers. If you quickly do it on your calculator, I think you'll get something like 1.37 or 1.38. And the reason it's not exactly the square root of 2 is because of anharmonicity. So a little bit of differences that we get because harmonic oscillator is not a perfect model for these cases. Okay, next let's look at HCl, HBr, HI. Vibrational frequency goes down. If I didn't tell you that the force constant goes down, your initial reaction might be, well, it's because we're putting a higher mass into the system. But if you calculate the reduced masses, you'll see they hardly change. For HCl, it's 1 times 35 over 36, or about 0.97. For HBr, it's 80 over 81, or about 0.99. For HI, it's 127 over 128, or 0.993, or something like that. So all of these have almost reduced masses of 1 in atomic units. And so the majority, in fact 99%, of the frequency change comes from the change in the force constant. Okay, well, we've had some discussion of molecular bonding for HF, which I didn't include here, HCl, HBr, HI. Hopefully, at least many of you would be able to tell me why the bond gets weaker as we go down this list of halides. When we have fluorine, we have the 2p orbital bonding to the hydrogen 1s orbital. When we have chlorine, we go to the 3p, bromine has the 4p, iodine has the 5p, and we get more and more of a mismatch in size of trying to bond that poor little hydrogen 1s orbital to a big p orbital. And so that's why the bond gets weaker. It's just chemistry. They're not getting as good overlap between these systems. And here, in some cases, I also list the bond distance. So you can see the HBr bond gets longer. Again, here we're trying to bond to the 4p instead of the 3p for HCl. I don't remember the HF bond distance, but I think it's 1.0 something. And HI again gets larger. Okay, next I'll put in a bunch of diatomic molecules that are heteronuclear, but the two atoms are either slightly different or they're the same. And I'll pick carbon monoxide to have a triple bond. You can see its frequency gives us a force constant of 18.7. Nitric oxide has a bond order of 2.5, 15.5 for the bond force constant. O2 has a double bond, as you remember. It's got two antibonding electrons. Force constant 11.4, and you go to fluorine, it drops way down to 4.5. So notice this is by no means linear with respect to bond order, but when you do look at the bond order, it gives you a good feeling for how strong a particular bond should be. Okay, so my main purpose of showing you this table is the value of understanding force constants. I'm showing you these for diatomic molecules, but many, many people for many, many decades have done force constant calculations for larger molecules, and these have helped to predict structures in new systems, and they've also helped to get a better understanding of when bonds get weaker or stronger when you do substitution into organic molecules, for example. Okay, last example, 3 diatomic molecules, Cl2, Br2, I2. In chlorine, you're bonding the 3p orbitals to each other, bromine 4p orbitals to each other, iodine the 5p orbitals to each other. The reduced masses drop in each of these cases, but so do the force constants. As you get larger and larger orbitals and more diffuse, farther apart, and you try to put them together, the bonds can't be pulled in as tightly, and you just get weaker bonds. I think your book also gives you other values of force constants for diatomic molecules. You'd actually be amazed, I think, if you go to the literature. There are, I would guess, 300 or 400 diatomic molecules that you can get vibrational frequencies for. Hg2 exists, 2 mercury atoms bonded together, just lots and lots of these. I have a question about class this Thursday. Yes, I meant to say that at the beginning, but a number of people weren't signed in then quite at the beginning anyway. We have class this week, Monday, Wednesday, Thursday. So pretend Thursday is Friday. So if you hope spring break would get you out of a Friday class, no such luck. Okay, so that part is pretty easy. Most people do the vibrational problem quite well on the exam. But the next part I go to is now one that a number of people have problems with. Okay, I have a question. If we're to plug in the values to calculate K as practice, do the units work out where K is millidynes per angstrom, or do we have to convert to millidynes per angstrom? A millidyne per angstrom is the same as 10 to the 5th dynes per centimeter. So if you do everything in gram centimeter second units, you get a 10 to the 5th on those numbers that I gave you. If you put everything in kilograms and meters, then you'll get 100 times the millinines per angstrom to get newtons per meter. That's an important question. So it's also why many of us still stick to CGS units, even though the official international unit is supposed to be MKS, meter kilogram second units. Okay, so I recommend thinking about the next topic very carefully, because a lot of people have problems with this next part. I always argue what I'm going to talk about is going to be arithmetic, just simply addition and subtraction, but just getting the picture of what's going on for a lot of people gets to be confusing. Up to now, we're saying that we can look at rotations individually, we can look at vibrations individually, but if we actually record a spectrum of something like HCl or carbon monoxide, what we see are the vibrational rotational spectra, meaning both kinds of energy levels are changed at the same time. And so our model is going to be that you can just add the vibrational and rotational levels to figure out what the quantum states are. You remember at the beginning when we talked about molecular rotations, we used the rigid rotor model. We said rotations and vibrations don't interact because rotations are about 100 times slower. But here we're now saying when we actually record the spectra, you're going to see both of these at the same time. Okay, so unfortunately, well, I guess it didn't go off. Okay, now everybody can see the formula. So our vibrational model is going to continue to be the harmonic oscillator model, and the rotational model is the rigid rotor model. We go back to our Schrodinger equation, our time-dependent Schrodinger equation. It gives us selection rules. And in addition to the fact that you have to have a dipole moment change for infrared spectra, we find that the quantum number for rotations, delta J, has to increase or decrease by 1 unit. Delta J cannot be 0. Delta V is still 1 from the harmonic oscillator model. So what this means is you cannot look at a pure vibrational transition for a molecule like carbon monoxide. You're going to have to either increase or decrease the rotational energy to see it. And obviously then to interpret the spectra, you have to be able to understand what the selection rules are. For Raman spectroscopy, the selection rules are different. Delta J can be 0 with no change in rotational energy. Or if you change rotational energy, it has to go up by two quantum states of J, or down by delta J equal to 2. Delta V is still equal to 1. In terms of nomenclature, if we had delta J0, we're going to call it a Q branch in the spectrum. If we have delta J plus 1, increasing the rotational energy, we call it an R band. If delta J increases 2, we call it an S band. So you see we're alphabetical, Q, R, S. I'm not sure quite why Q was picked in the middle. Maybe people initially put a 0 there as to the midpoint, but then to make sure it wasn't a 0, they turned it into a Q. Okay, and we also have options to delta J minus 1, then it's called a P band, and then for delta J minus 2 in Raman spectra, we call it an O band. And so that again gets a bit confusing with the Q's and O's. Okay, so I'm going to show you this diagram, but before I describe it, let me point out this lowest part is what we talked about when we talked about pure rotation. We had transitions 0 to 1, 1 to 2, 2 to 3. We had no change in rotational energy. What I'm going to show you here, this is quantum state for vibration V equal to 0. So no vibrational excitation down here. And we go up to quantum state V equal to 1 in the vibrational state. So to show you what we're doing, we'll go back here. So as far as vibration goes, we go from V0 to V1. So we're going to have that change in vibrational frequency. In rotational energy, I have to go way back to the beginning of rotational spectra. And here's our diagram. So this is the lower part of the diagram that I just showed you for rotational vibrational spectra, and I'm going to go back to that. So notice this is all for quantum state D equal to 0. So the lowest vibrational state, but we have J quantum numbers 0, 1, 2, 3, 4, and 5. Okay, so back to our vibrations. So please try to make sense of what's going on here. So a selection rule for infrared spectra, that's all on the left here that I have. This would be a J0 to 1 transition, so delta J plus 1. So everything on the right is what's called an R branch. 0 to 1, 1 to 2, 2 to 3, 3 to 4, and so on. So the J quantum number changes are the same as we had when we purely talked about rotational spectroscopy. But before, we were going 0 to 1 all in the D equals 0 state. Here we're also adding the vibrational energy. I should point out that these rotational spacing in this excited vibrational state, for our purposes, are identical to what they are in the ground state. They're not quite exactly the same, but close enough that for this course we'll say they're exactly the same. So when we have the 0 to 1 transition, this means it changes by the vibrational frequency, which for HCl would be 2886, plus 2b, 2 times the rotational constant, which for HCl would come out to be at about 21. So for HCl, this transition is 2886 plus 21, or about 3007 Wayne numbers. The next transition, going from 2b rotational energy to 6b rotational energy, gives you a net increase of rotational energy of 4b. So you would wind up with something like 3028 Wayne numbers, if I did it correctly. So the net result in the spectrum you're going to see nothing for delta J equal to 0. So that's what this dotted line represents here. But to be away, on the high side, you see what's the band called R0. This is all the R branch. The subscript says the level that you're starting from. J0, you start from, you go up to J1. All these spacings are 2 times B. Well, I chose you 4B in the center from the first band here to that one, is the first P band starts at 2B and goes up to the upper vibrational level with no rotational energy. So this first transition is the vibrational frequency minus 2 times the rotational constant. And thereby you get a separation of 4B. Okay, well, I think that's pretty hard to absorb during a lecture, so I very strongly urge you, when you go home, you look at this diagram, and then you compare it to a spectrum that you get, and this is what it winds up looking like. Later on, I'll show you a spectrum of HBr, which is more typical of what you usually see where absorption comes down. I like to show the carbon monoxide spectrum, and the book I took it out of shows it as an absorbance spectrum. What you did in organic lab, almost certainly you had the peaks come down. So it measured the amount of absorption coming down. This is absorbance going up here. All right, well, you see a gap in the center. So if you exactly average the space between these two bands, that would be your pure vibrational frequency with no rotational changes. If we go to the right, notice the frequency scale increases to the right. This band is labeled R0. This first band for CO would be the vibrational frequency of carbon monoxide plus 2 times its rotational constant. Next one would be frequency plus 4B. Next one, frequency plus 6B. All these spacings would be 2 times B. You can see how beautifully it's all spaced. All these spacings look basically exactly the same. On the low frequency side, the first frequency is 2 times B less than the vibrational frequency. So the spacing between the two center bands is 4 times B. The next one here is 4B lower than the vibrational frequency, 6B, 8B, and so on. And some of these R bands and P bands are labeled. So this was R0, this would be R1, R2, R3, R4, and so on. One more feature I want to show you. Natural abundance of carbon in nature is about 1%. So 1% of carbon monoxide is carbon-13 monoxide. If you look down here, you see some bands right there. The center of the carbon monoxide with carbon-13 vibrational band is right here. And then you see some rotational structure for it. But it's only 1% of the other. And so it looks like it's a lot less when you compare the intensities. But study the spectrum, make sure you can correlate it with what this looks like right here. All right, well, we aren't quite out of the woods yet because we also have to see what happens in Raman spectra. Okay, Marco asks why the decrease in absorbance at the extremes. And I was hoping you would remember that from pure rotational spectra. When we look at these levels, you remember the intensity is proportional to the number of molecules in each quantum state. And so that's equal to the transition moment integral, which comes out to be just about the same for all of them. But then we have population changes. And you should have remembered that we have a degeneracy factor. So for J0, the degeneracy is 2J plus 1, which is 1. For the J equal 1 state, 2J plus 1 becomes 3. The next level is 5, then 7, then 9, then 11, then 13. But then the question is, why do we get a decrease? The decrease is also proportional to the exponential term. So if we're at J equal to 6, the energy of that state is 6 times 7 times B, or 42B. For HCl, that would be about 850 Wade numbers. And KT at room temperature is 207. This is probably not being observed by you, but it means you get an exponential term of e to the minus 4th. So as you go to higher and higher states, when you start from P17 to P18, you're way up in energy, and that exponential term starts killing you and going way down. As it turns out, both carbon and oxygen have relatively heavy masses, 12 and 18. They may not seem high, but compared to hydrogen and 1, they give you a fairly large reduced mass. And so the rotational constant for carbon monoxide is very small, and a lot of these energy levels are closely spaced. So that's why you can get up here to something like a transition from J25 or something like that. But the increase is due to the degeneracy factor. The decrease is due to that temperature, the temperature term, which makes higher levels be less populated. All right, well, we have time just to look at the Raman transitions. We can have the Q branch. So all of these transitions, J0 to 0, 1 to 1, 2 to 2, should ideally have just about exactly the same frequency. And then we can have an S branch with J increasing by 2 units, so 0 to 2, 1 to 3, 2 to 4. If you do the calculations, you'll find J0 to 2 transition goes up 6B. Then the next one is up 10B, then 14, then 18, and so on. So these would be called the S bands. We'll start off with this next time on the Raman spectra. I have to jump quite a bit ahead. But here's the Raman spectrum that you basically see. Well, this is for pure rotation, and this is for rotational vibrational spectra. So you see a Q branch in the center, and then S bands increasing to the right. This is 4B higher than the Q branch, then 10B, 14B, 18B, 20B. So beautiful 4B spacings that we have. I have a chat question before we stop. Okay. Okay, I think I've answered all the chat questions. Okay, well, on Wednesday, we'll go back and continue here talking about the Raman spectrum. As I said, our next exam is in 2 weeks. So where I expect us to get to is through our discussion of vibrational spectroscopy, but we won't be able to get into electronic spectroscopy, which will also be covered on the third exam. Okay, that was one more question. There was, what is the end of exam 2 material? As of now, it'll be at the point where it says electronic spectroscopy. We will not get into electronic spectroscopy. I'm not sure if we'll quite be able to finish talking about polyatomic vibrational spectra, but I think we will be able to finish that. There are a lot of practice problems on calculating force constants, rotational vibrational spectra, and so I strongly recommend that you get started on doing some of that also. Okay, so happy Ides of March.